The strange man at right wants to pull the two blocks to the other side of the room in as short a time as possible. However, he doesn't want the top block to slide relative to the bottom block. The coefficient of friction between the bottom block and the floor is 0.25 for static and 0.2 for kinetic. And the coefficient of friction between the top block and the bottom block is 0.3 for static and 0.25 for kinetic. The blocks start from rest. So let's start off by doing a free body diagram for the top block. I have the perpendicular force, which is a normal force, but in this problem I'm going to have two normal forces, so I'll just call it the force that the bottom block exerts on the top block. I have the force of gravity acting downwards. This is the force of gravity for the top block. That's the mass of 50 times 9.8. That is 490 newtons. The bottom block touches the top block. If there was no friction, the bottom block would move out from underneath, and relative to the bottom block, the 50 kilogram block would be moving this way. So it'd be sliding on the bottom block, and the relative motion would be this way. Because it doesn't move relative to the bottom block, there must be a force going this way. This is the force of static friction between the bottom block and the top block. But not only that, if he's going to pull the blocks across the room in a short amount of time as possible, this must be at its maximum value. So if he pulled any harder, the top block would slide off of the bottom block. So then we can do the free body diagram for the bottom block. We have the force of gravity for the bottom block acting downward. The mass of the bottom block is 150 kilograms. And so this force of gravity is 1,470 newtons. And we have the force that the rope exerts on the bottom block from the strange man pulling on the rope. So let's call that F pull. That is horizontal. And we have the force that the floor exerts on the bottom block. This is a normal force. It's perpendicular to the surface of contact. I'll just call it the force that the floor exerts on the bottom block. And because the bottom block is sliding on the floor, we have a force of kinetic friction acting to the left. And now, by Newton's third law, if the bottom block exerts a force on the top block also exerts a force on the bottom block. These forces have the same magnitude but are pointing in opposite directions. Since they're a pair by Newton's third law, I will connect them with a dotted line. Also, the force of static friction that the bottom block exerts on the top block is a pair with the force of static friction that the top block exerts on the bottom block. So these forces have the same magnitude. But are acting in opposite directions. Okay, so for the bottom block we have two forces from the top block, two forces from the floor, a force of gravity, and a force from the rope. Okay, so I'm going to start off by looking at the top block. And I'm going to do Newton's second law in the y direction first. So this is the sum of the forces in the y direction. The top block is not moving in the vertical direction, and so the sum of the forces in the y direction is equal to 0. This means that the forces in the y direction balance. So the force that the bottom block exerts on the top block is 490, and by Newton's third law, the force that the top block exerts on the bottom block has the same magnitude. So we found two of our unknown forces. And now if I look at the sum of the forces in the x direction, that's equal to the mass times the acceleration in the x direction. And I have one force acting in the x direction. That is the maximum value for the force of static friction between the bottom block and the top block. The mass is 50 kilograms. I do not know what the acceleration is. I can figure out what this maximum value for the force of static friction is between the bottom block and the top block. Okay, so between the bottom block and the floor, so we don't want to use that. Between the top block and the bottom block, we have 0.3 for static and 0.25 for kinetic. Because the top block is not sliding relative to the bottom block, we want to use the 0.3 for static friction. And the maximum value for the force of static friction, and this is between the bottom block and the top block, is equal to the coefficient of 0.3 times the normal force. We have friction between the bottom block and the top block. We have friction between the floor and the bottom block. If we're looking for the friction between the bottom block and the top block, we want to use the perpendicular or normal force between the bottom block and the top block. So this is FBT, and that force is 490. And so for the maximum value of the force of static friction, we have 147. So now I can go back to what I have here, and I can find the acceleration in the x direction. That is the maximum value for the force of static friction between the bottom block and the top block, divided by the mass of 50. And that gives me 2.94 meters per second squared. Let's add some units in there also. All right, so this is great. I know all of the forces which were unknown here, and I know this acceleration, and because the top block is not sliding off of the bottom block, the two blocks have the same acceleration. So now, when I look at the bottom block, I already know the acceleration that the bottom block has. But let's look in the y direction first. So if we have the sum of the forces in the y direction for the bottom block, there's no acceleration in the y direction. So now if I look here, I have two forces going downward and one force going upward. If they're going to add up to give me 0, the upward forces must be equal to the downward forces. So I have 1470 plus this force, which is 490, is equal to the force, the normal force that the floor exerts on the bottom block. And that is 1,960. This force is equal to 1,960 newtons. Before we move on, we're going to need this force of kinetic friction. So I can say the force of kinetic friction, now be careful. This is between the floor and the bottom block. So between the bottom block and the floor, we have 0.25 and 0.20. We want kinetic friction, so that's 0.2 times the normal force. That's between the floor and the bottom block, so that's the 1,960. And that gives me, for kinetic friction, 392 newtons. Okay, and then I can look at the sum of the forces in the x direction, which is equal to the mass times the acceleration in the x direction. I already found the acceleration in the x direction, and the mass is 150 kilograms. Some of the forces in the x direction, I have the force of the pole, and then I have the force of static friction, which I found here to be 147, acting in the other direction, so that's minus 147. Then I have the force of kinetic friction between the floor and the bottom block, which is 392. And that is equal to 150 times 2.94. And I get the force of the pole is equal to 150 times 2.94, then bringing the 147 and the 392 over to the other side. And that gives me 980 newtons. for the force of the pull. So let's just make sure we found all of the unknown forces. So I have the force between the bottom block and the top block, the force of static friction, I have my acceleration, I have this force between the floor and the bottom block, I have my force of kinetic friction, and I have the force of the pull, and I already found the magnitude for the force of gravity for the top block and also for the bottom block. And there's not any kinematics to do here because you don't know how far he has to pull the block, so it says in as short a time as possible, but we don't know how far he's going. So we found everything that we could find. So the last thing that you could do here is check to make sure that the blocks are actually going to move when you pull on them with a force of 980 newtons. So you could use the maximum value for the force of static friction between the floor and the bottom block, which comes from using the 0.25 that they give you here. And if you use that coefficient to find the maximum value for the force of static friction, and you have a net force going this way, then the force of the pull is large enough to overcome the force of static friction and the blocks will move. So let's do this just as a little bonus. The maximum value for the force of static friction between the floor and the bottom block is 0.25. The normal force was 1,960. So this gives me 490. That should be larger than the force of kinetic friction that we had here. And if the acceleration is 0, you have the force of the pull. Some of the forces in the x direction would be equal to 0 if it's not moving. You have the force of the pull, which we said was 980 newtons, minus this force of static friction between the top block and the bottom block, which is 147, minus the maximum value for the force of static friction, which is 490. But because 980 is greater than 147 plus 490, you will still end up with a net force this way. So this is supposed to be equal to 0, but it's not. So we have 980 minus 490 minus 147, which is 343. So you still have a net force going this way, which means that the force of static friction, the maximum value for the force of static friction, is not large enough to keep the boxes from moving. So that's good. So yes, we can say it does move if they start from rest and he exerts a force of 980 newtons.